Hi folks, Mrs. Gates here. I want to give you some instructions on the lab we will be doing this week. It's about objects on inclined planes. Inclined planes is just the fancy physics way of saying a hill. But before we get into those specifics, I want to talk about a little bit of background information. Before we get into what happens with objects on inclines, let's review the forces that are acting on an object on a flat surface. If you consider the object shown here, you would probably say that there is a force of gravity and a normal force acting on this object, and that if it's remaining stationary or traveling at a constant velocity, those forces would be equal to each other. You would probably draw a force diagram that looks something like this, with the force of gravity directed down and the normal force pointed up. If you wanted to actually measure the force of gravity on an object, you might put it on a balance. Here we have a blob of Play-Doh that we will be using as we go through this lab. You can see that on the balance, its mass registers at 331.5 grams, or 0.3315 kilograms. To calculate the force of gravity, we multiply the mass in kilograms by 9.8 and end up with 3.249 newtons for our force of gravity and for our normal force. But how does an electronic balance work? What is it actually measuring? If you think about the mechanism inside of the balance, all it can really measure is the amount that it is pushing upwards. The balance, in essence, only measures the normal force that it is exerting on any object. It then converts that force into grams and records the mass of our object. Throughout the course of this lab, we will be using a balance in order to measure the normal force exerted on an object as it sits on a ramp. In our lab today, we will be considering several objects sitting on inclined planes. Take a second and consider a blob of Play-Doh sitting on a ramp. On a piece of scratch paper, draw a force diagram for the Play-Doh. Your force diagram should look something like what's shown here. The force of gravity should be pointing directly down towards the center of the Earth. The normal force is always perpendicular to the surface, so it should be pointing up and slightly to the left, perpendicular to the surface of the ramp. The force of friction is what's holding this Play-Doh in place and keeping it from sliding down the ramp. The force of friction always acts in a direction parallel to the surface. The purpose of this lab is to investigate each of these forces to see how they change as the angle of the ramp increases. In part 1, we will be looking at how the normal force on a piece of Play-Doh changes as the angle of the ramp increases. In part 2 of the lab, we will be using a frictionless lab cart held in place with a spring scale in order to look at how the force of tension varies as the angle increases. As you collect data from the images in this lab, you will notice that we are measuring the angle of the ramp using a protractor affixed to the top of the ramp. There is a plumb bob hanging from this protractor indicating straight vertically down. This enables you to measure the angle on the protractor as follows. The red line shows where the plumb bob is located. The black line goes to the 90-degree mark. The angle in between these lines is the same as the angle on the other side of the triangle, between the ramp and the countertop. In this case, that angle is about 15 degrees. To collect data for this lab, you will be analyzing the pictures on several slideshows. For part 1, you will collect data on the angle of the ramp as well as the reading on the balance in order to determine the normal force acting on the Play-Doh. For part 2 of the lab, you will collect data for the angle of the ramp along with the reading on the spring scale telling you the force of tension that is holding the car on the ramp.